Okay, apparently some people could see the slides before, but now hopefully they can see they can hear as well. So, I'd like to introduce Dennis Prangle, who's going to talk about lazy ABC.
Okay, thanks very much, Rich. So anyone who came to this meeting last winter, this is actually a talk on the same topic, but I've changed the name of the method since then, after some feedback that it was too boring last time. Right, okay, so to start with a bit of background on likelihood-free inference and ABC. So Christian's already covered a lot of this. Hopefully I'll be able to go through this quite quickly. Okay, so generally Bayesian inference is based on Bayes' theorem. The posterior is proportional to the prior times the likelihood. So we're interested in some parameters theta. And we'd like to learn the posterior distribution conditional on some data, which is going to be labelled y obs here, because we'll also have y without a subscript to refer to some other generic data sets that aren't the observed ones. Lots of Bayesian inference methods require repeated numerical evaluations from a likelihood function, L of theta, which is evaluating this probability density of the observed data at particular parameter values. However, for lots of models, the likelihood function is intractable. So by intractable, I mean either that it's impossible to numerically evaluate the likelihoods, or that it is possible, but it's impractically expensive. So it will take maybe a couple of hours of computer time to evaluate it. Christian's talked about some examples, and these are some areas where likelihood-free methods are used quite a lot. Population genetics, epidemic models, systems biology, and there's a lot of interest recently in agent-based models. So this is a general scheme for likelihood-free inference. General scheme for, I thought that was this. Going wrong for a second. So this is a general idea for doing inference without the likelihood function. ABC is a special case of this. So what you do is simulate lots of data sets, represented by y's, conditioned on lots of different parameter values. So a key thing is you have to be able to simulate data sets, and that's what we're using as the engine for inference instead of evaluating the likelihood function. We compute some sort of distance between our simulated data sets and the observed one, and then we base the inference on the parameter values such that the simulated data sets have small distances, so appear to be good fits. So there's many different ways you could do this. You could start off by simulating this, coming up with some thetas, then get the y's and so on, or you could kind of interactively choose new thetas depending on what the algorithm's done so far. So this is a very simple algorithm implementing that scheme, and this is basically the simplest possible ABC algorithm. So it's a version of rejection sampling. And we're going to iterate over these three steps lots of times. We sample parameters from prior distribution, simulate some data conditional on those, work out some sort of distance between the simulated and observed data sets, and accept if it's below a threshold h, which has to be pre-specified. And then as output, we get a sample of some accepted parameter values. And you can look at the distribution of these parameter values, which Christian showed as well. So this is the distribution. This is an ABC approximation to the posterior distribution. And what we've got is parameter values drawn from the prior, but then also conditions on data sets that are generated having a distance to the observed data below a threshold. And hopefully, if we've chosen the distance well and the threshold is small, this will be approximately equal to the true posterior of interest. So you can actually prove if you've chosen a sensible distance function that as h tends to 0, this does converge to this distribution. So we have got around not being able to evaluate the likelihood function, but the price that we pay is that we get an approximation to the posterior, and this is quite computationally intensive. So we've had to simulate a lot of data sets usually. So this is a very simple algorithm, and lots of work has been done on lots of different, improving lots of features of the algorithm, doing more intelligent things at basically all of the different stages. I'm going to focus in this talk on improving the computational cost of the algorithm. And hopefully this is very complementary to all these other things you can do to improve the efficiency of the algorithm. So the motivation for the method is that ABC needs a large number of simulated data sets to be produced. Do we really have to do all of those simulations, or could we save some time by not doing all of them? Most of the simulated data sets are poor matches to the observed data in the end, and end up being rejected and not used in the outputs. Sometimes we can tell early on during a simulation that it's probably going to be a poor match. So can we just reject the simulation at that stage and save some time? And this talk is based on work in 2 papers. So a paper called Lazy ABC, which is going to appear in Statistics and Computing. And this is a short, this is a conference paper which reviews this, summarizes the methods in this paper and gives a slight extension.
Does it converge to anything?
Yeah, so the next one will be laziest, yeah.
And then you stop.
Yeah, so if you want to look at these papers, this one's only 4 pages long, so it's a much quicker read. Okay, so I'm going to talk about the lazy ABC algorithm, some properties of the algorithm, how it's tuned, and then give an example. So the idea of the algorithm is the simulation will be split into 2 stages. So Y is the data, but the first stage is going to simulate something called X, based on parameter values. This is the initial simulation stage. And X is some complicated object that encapsulates all the details of a simulation up to that point. The second stage will then carry on. Given X and theta, it will complete the simulation to give us Y. So there's lots of freedom of what the initial stage could be. It could be a sort of pre-specified point at which we stop, which we consider stopping, or it could be a random event. So I'll try and illustrate that. So a very simple illustration is that we might have a process like a random walk. And all that's actually observed is the endpoints. And then we try to learn about the parameters of a random walk, for example, the drift and the variance, through ABC. So we perform lots of simulations with different parameter values and try to see which ones come close to recreating the data. So with lazy ABC, we want to save some time by considering stopping this random walk early. So we might say, let's stop at this time point, consider where we are, or the path so far, and see if we think it's likely that we're going to hit this point. So that's what I mean here by the initial stage is a pre-specified set of operations. It's everything up to this time point. Well, the second one is we could perhaps set a boundary, and, or maybe down here as well. If our simulation ever crosses this boundary, then that could be the initial stage. We'll consider stopping, and the continuation stage could be carrying on from there. So we'd like to reject if the initial simulation looks unpromising and save the time of doing the second stage of a simulation. So I think a simple option is just deterministic stopping. We stop according to some rule. The problem with this is that earlier on we had this expression for the ABC posterior. If we also condition on x obeying some rule, that's an extra thing to condition on in this density. And that could make the approximation a lot worse. There would be some cases in which it wouldn't. But in general, we'd like to avoid that problem. So it turns out a way around the extra approximation error is to use randomized stopping instead of deterministic stopping. So what we've got is we introduce a probability of stopping, or probability of continuing rather, and that's a function A of the parameter values and x, so the state of a simulation when we consider stopping. Most of the time, this continuation probability has to be non-zero, so it always has to be some chance of continuing. And intuitively, we want this probability to be low if the simulation so far is unpromising. If the simulation does end up continuing, we want to upweight the results to balance out all the simulations that got left out. I'll go into more detail about exactly how that's done later. It's quite important to tune this function well, and also that comes up later. So this is the actual algorithm. It's basically the same as the earlier ABC rejection sampling algorithm with some extra steps. So as before, we sample some parameter values from the prior. Now we just do the first stage of the simulation and calculate our continuation probability. Then we draw a uniform random variable to decide whether or not to continue. So with probability equal to our continuation probability, we'll keep going. If we don't keep going, we're going to give weight of 0 to this iteration, so to this value of theta. And then we can skip to the end and start the next iteration, and that's effectively early rejection or early stopping. If we continue, we complete the simulation, work out the distance. If the distance is above our threshold, we reject as usual and set the weight to 0. If the simulation is close to the observed data, we'll accept and give it a weight of 1 over the continuation probability. So the output sample we get is a weighted sample of parameters and weights, which will either be 0 or 1 over the continuation probability. So this is upweighting the simulation, so that ones that were unlikely to continue get much higher weights than ones which were very likely to continue. Okay, so once we end up with a weighted sample, and there's standard ways we can do inference from a weighted sample. So if we want to find the expectation of some function, we evaluate the function at all of the thetas in the sample, and then weight it. We take a weighted average of those evaluations based on the weights that we've got. And this allows you to come up with things like parameter estimates, interval estimates, and histograms, and so on. So what can go wrong is if some of the weights are very large, they end up dominating the estimates. So this sum is mostly influenced by just a small number of thetas. So effectively, you've got a small sample size, and that's bad because you've got a very variable estimates. Okay, so lazy ABC and standard ABC have the same distribution in a certain sense, and that is when you take the number of iterations, you take the asymptotic limit of that being very large, the limits of these Monte Carlo estimates are exactly the same. So in this sense, ABC doesn't introduce any further, lazy ABC doesn't introduce any further approximations. So the proof of this is actually really short. It's just a couple of lines in the paper. And it's based on showing that the expected weights given a particular value of theta are the same in both algorithms. So this follows very much from work on the pseudo-marginal algorithm, which I think Christophe's going to talk about later. And so the key part of the algorithm that gives you these expectations being equal is that this probability of continuing So the expected weight depends on this realized weight of 1 over A and the probability of continuing, which is equal to A. And so AI and 1 over AI are going to cancel out, and that's really the key of the proof. So we've got this property of lazy ABC not introducing further approximations. That doesn't depend on the choice of our continuation probability function. However, if we choose a crazy continuation probability function, things won't work very well. What will happen is we'll converge very slowly to these values. So if we choose a crazy value of this function, where we're very likely to reject even for good samples, so we'll have A very close to 0, but we'll accept, and we'll end up with a weight of 1 over A being extremely large. We'll get some large weights, we'll get poor Monte Carlo estimates, and they'll very slowly converge on the correct values. So we've got this nice theoretical property, but it does depend on tuning the algorithm well. Okay, so in this section I'm going to talk about the tuning. You do also have to think about your standard ABC tuning choices, like which summary statistics do you use, what threshold do you use, and so on. And it might be worth investigating whether these interact with tuning for lazy ABC. But so far, I've only looked at this probability on its own. So what we want to do is choose this continuation probability to save time without getting too many large weights. And as I said, a large weight is if we get a good match after giving something a small value of A. So what we want is being unlikely to continue when we think we're going to get a poor match of the data in the end. And I think this is the wrong way around. I think A should be smaller for slow simulations. So if we've got something very time consuming, we want to be less likely to do the full simulation. So often it's possible to just come up with an ad hoc choice of continuation probability. Say that it's very easy to come up with some rule for your particular application, dividing the incomplete simulations into good and bad. We can always continue the good ones and have some smallish probability of continuing the bad ones. So then we've saved 3/4 of the time finishing the bad simulations, but our largest weight is only 4, which is not going to break the algorithm. So making this sort of ad hoc choice is very simple. And hopefully, a lot of the time, we've got enough intuition about the application that there's a very obvious way of doing this. So when you can't come up with tuning this way, there are some theoretical results as well. So this is the asymptotically optimal choice of the continuation probability. So it's the minimum of 1 and a number lambda times this fraction. So in the fraction, we've got 2 quantities. On the top, this is the probability of being the simulation being close to the observations, given the current points of the simulation and the parameters. So sorry, there's a typo here. This should be the distance between y and y-obs. So this means that when the probability of eventually hitting the target is small, our value of A is going to be small as well, which ties in with our intuition. On the bottom of this fraction, this quantity is the expected time remaining to complete the simulation, depending on where we are at the moment in the parameters. So when the simulation is going to be extremely costly, we also get a smaller value of A. So we've also got this complicated variable lambda, which doesn't have a nice closed form expression. So this ties in with the intuition earlier of these 2 facts. And it quantifies exactly how they should affect the continuation probability. And this is exactly what I mean by asymptotically optimal. Okay, so that's a nice result, but it's not obviously usable in practice. So you can try to estimate the optimal choice of A by doing some preliminary tuning simulations, so running the simulation, simulating lots of data sets for different parameters, and trying to estimate these two quantities in the ratio. Then the third quantity you need to get, that's only a scalar, so it's possible to try and do numerical optimization to work out the best value of that. And that gives us an estimated optimal choice of A. Then we could try and do that for lots of different possible stopping points and try to work out the best point at which to stop in our simulation. Okay, so this seems a reasonable scheme, but it turned out that some of the implementation details are quite tricky, so quite a lot of the papers is devoted to implementing this. Okay, so finally a short example. So this is an epidemic model. It's a compartmental model where individuals in the population are on one of three stages at any particular time. They're either still susceptible to the disease, they're infectious and capable of spreading the disease, or they're removed from the population. So at this point, they've had the disease and they're now immune to it. So any time the state of the population is summed up by the number of individuals in each stage or compartments, I'm fixing a particular initial state, and then there's probabilities of transitions of individuals transitioning between the two states. So the probability of infection depends on the population who could get the disease, the susceptibles, and also the size of the infectious population. Whereas the probability of recovery just depends on the size of the infectious population. And in this very simplified version of the model was just one parameter, R0, which is talking about the relative probabilities of these two things. The data is just the number recovered in a sample of 100 taken at the end of the epidemic. So for this very simplified example, ABC is not really necessary. You can do all this exactly. However, ABC is commonly used for more realistic variations on this kind of model with many more details, which end up making the likelihood intractable. So in this example, I consider stopping after 1,000 transitions, so that's quite early in most epidemics, based on the number infectious at that point. And this is, I did one of the tuning methods, and this is the continuation probability I came up with. So in this range of around about 1,300 infectious, we're certain to continue the simulation. So they look like very promising values. And then away from that range, the probability drops off quite quickly. So we're not allowed to have zero probability, but on this figure, we're so close to zero that we can't see the difference. So I performed 10,000 iterations of ABC with quite small acceptance thresholds. I did this with standard ABC rejection sampling and lazy ABC. And I used the same random seeds for the simulations each time. So both times, say for the 5,000th simulation, if the simulation is continued to the end, we'll get exactly the same simulation for ABC, standard and lazy ABC. So the two methods ended up accepting exactly the same parameter values, which is good. Almost all of the lazy ABC weights were 1. A couple of 5 of them were greater than 1, but were still quite small. They're all below 3. So that means almost all of them were in this range here, and a couple were slightly further out into the tails. So that means that the inferences we get from the two methods are almost identical. However, lazy ABC took a third of the time, basically, of standard ABC. And then the papers have much more detailed comparisons of the two methods on a more complex application. Okay, so to conclude, lazy ABC saves time by abandoning lots of unpromising simulations during ABC. It doesn't affect the ABC targets in a particular sense. It should be quite easy to implement using an ad hoc tuning method, but there's also a more sophisticated tuning approach, which will get you closer to optimal performance. There's some further work in the paper. So in the approach that I've mentioned, you had to, of the example that I showed, you had to know that your acceptance thresholds in advance. A lot of the time in ABC, you do this during the analysis. There is a way of doing this within lazy ABC. I also talk about how you can use this with importance sampling rather than rejection sampling. And you might want to consider having multiple stopping decisions during your simulation. So in the paper, I show that this will work. You can come up with an algorithm to do this that has the right targets, but tuning it optimally is a lot more complicated. So there's only a couple of really special cases where I've got results in the paper. Future work includes things like the best way of applying this to MCMC and SMC algorithms, learning a good distribution of when to continue the simulation adaptively, rather than having to have a pilot stage and then a main stage. And there's various related approaches in the literature that it would be nice to compare to, things like delayed acceptance, MCMC, and the pre-processing approach that Christian Robert and other people have been working on. Okay, thank you very much.
Okay, any questions?
So I've got a couple actually. One is, when you drew the picture on the board, it looks a little bit like you're kind of using prior information almost of what you expect the path to look like to inform your choice of when to decide whether to start.
Yes, exactly, yes.
So is there a kind of argument that you should really just be using a stronger prior?
So what I'm really doing is, or you could view this as you're placing a importance weight on theta and x. So it's very similar to doing a stage of rejection sampling to get up to the stage where you've got theta and x, and then doing importance sampling. So yes, you can very much view this as importance sampling, and you have to choose a particular importance weight to use.
My other one was a bit more technical, which is just about, you're talking about as long as you correct the fact that if you accept proposing for the weight, then you still get kind of consistent estimators for expectations of interest. Obviously, in normal, ordinary Monte Carlo, you get more than that. Often you get central limit theorems and things like that. Is there anything, I guess, have you got similar things? I mean, I guess if you chose the weights in the wrong way, you might not get that in this circumstance.
That's a good question. I don't know. So there's lots of other papers on this algorithm. It's basically an importance sampling algorithm, and you end up with this sort of weighted sample at the end, where the weights are random as well. And there's several papers on this kind of algorithm, things like the importance sampling squared paper. They might have results on central limit theorems, but I can't remember them off the top of my head. So it would be interesting to look at those and see if the central limit theorem always holds, or if for some conditions the weights have to be fairly sensible for them to hold. So that would be interesting to look at. Yeah, Christophe.
Yeah. So this is very much related to rare event simulation in a way. And there's a whole literature about it. In particular, you run a Markov chain and you want to target a given endpoint or something like that. So, and people have used sequential Monte Carlo methods to do that. And in this situation, there's no interaction between your simulations at all, which is good in terms of computation because you can give it to a bunch of parallel algorithms and computers. But have you thought about trying to make them interact? Okay, which would mean that the algorithm wouldn't be lazy anymore, but you would reallocate your simulation to the promising simulations. That is, a given X could have several descendants. You see what I mean?
Yes, that makes a lot of sense. So the short answer is I'm just thinking about that at the moment.
Right.
But yeah, it would make sense to have a kind of particle filter or SMC algorithm where you step through the simulation, and as you get to each stage of a simulation, you might resample based on how good you think the simulation's been so far, and have several continuations of a good simulation and downweight the poor ones.
And you would know what your cost is, because here it's going to be random.
Yes, so it's definitely random here. Would you definitely know what the cost is if you do it like this?
Yeah, it could be approximately fixed. And at each iteration.
Oh yes, your number of particles. Yeah. Yes. Yeah, that's true. There's a paper by Lawrence Murray and Pierre Del Moral where they look at they're trying to do SMC for where you've kind of got a very big jump between two states, and they're building a bridge in between and doing it in lots of stages. And I think there's a big link between that and what I'm doing here with lazy ABC. This could be viewed as an ABC version of that sort of approach, where at the moment we've only got 1 point in the bridge at the middle. But yeah, I think it's a very, very promising thing to try. And it might tie into learning these adaptively. Yeah, I think there's a question at the back. Yes.
I just thought that is anybody doing something using evolution computation? It looks like you can use the generate a random solution in space, and then you just pick up the best. So you have instead of generating one figure, you actually have a population of figure. Then you can actually find the trajectory that the
yeah, so this is very similar to the whole idea of likelihood-free inference. We get a whole population of.
So at the moment, you're only one at a time. So if you use evolution, you have a lot of figure.
Ah, okay. So you can. I can't find the algorithm now. You can. So there's n steps here, and you could run them all in parallel, or several of them in parallel. And as Christophe said, you could have some kind of interactions between them as well. So there's definitely ways to improve this algorithm by doing steps in parallel and things like that. Yes.
Yeah, I was going to ask. In this case, you've got your H sort of, which is homogeneous across all the different possible observations. Say for some biological communities, you might be modelling stock numbers, and you would want to absolutely eliminate something that wiped out a species that you know exists, no matter how close it was with all the others. So you could implement that by rule, in a sense, stopping the simulation once any of those species was wiped out. Can you simultaneously do that and apply this lazy algorithm?
Yeah, so I think there's a couple of questions or a couple of points in there. Okay, so within this ABC algorithm, you're calculating a distance and rejecting if it's below a threshold. That distance could be a really complicated function. So you might compute your distance with it in two components. One of them is this really important condition you mentioned. And if that's violated, you could say this distance is infinite, and you're definitely going to reject. So that's how it would work in standard ABC. And yeah, then you could fit that into lazy ABC any way you wanted. You could focus on, after a few steps, you could focus on either components of the distance, and you use that for your stopping criteria. So it might be using this most important criteria might be a good way of stopping very early in some applications. Does that answer the question?
Yes. Yes.
Okay. Good.
Thank you.
Good.
No, that's all I wanted to know.
Okay. Okay. Thank you very much.
Okay. Thanks a lot.
Okay, you're that one. Yeah. Okay, let's see. Oh, yeah. Right, okay. If we can find the point. Oh, sorry. Oh, yeah. Sorry. Go on, you said that. Yeah. Okay.
That's good.
Right. Okay, that's nice. I'll try it myself. Okay. 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 So next up is John Hemmings from Wessex Environmental Associates.
Hello, yes, I'm affiliated with the Wessex Environmental Associates group, and I'm going to talk to you about some work that I did under the NCEO carbon cycle theme when I was at the National Oceanography Centre. My co-authors in this work are Peter Challoner from Exeter and Andrew Ewell from NOC. And we're also indebted to Andrew Coward and the NEMO development team at NOC for help with the global model. The context of our work is the global carbon cycle, and the specific focus is on the export of carbon via biogeochemical processes into the ocean interior. So this bit here. That's put at about 13 gigatons of carbon per year in this estimate. The black arrows here show pre-industrial carbon fluxes, and the red estimates are the anthropogenic change. The total anthropogenic emissions from fossil fuel burning and land use changes are put at about 9 gigatons per year, and about 2 gigatons of this is taken up by the oceans and a similar amount by terrestrial systems. The net uptake by the ocean is controlled by a combination of biological and physical processes, and any change in these biological or physical carbon pumps can introduce important feedbacks which may affect the climate in the future. There's considerable uncertainty in the likely impact of climate change on ecosystems and biogeochemistry in the ocean. One of the challenges for the ocean biogeochemistry models is to be able to predict changes in the biological carbon pump under different climate change scenarios. The biological pump is a collective property of complex phytoplankton-based food web. Phytoplankton, through photosynthesis, take up carbon in the sunlit zone, and this primary production process reduces the PCO2 at the sea surface, causing more CO2 to be drawn in from the atmosphere. A lot of this carbon is then recycled through community respiration and goes back into the atmosphere on seasonal timescales, but a small fraction of it is exported into the ocean interior, primarily by sinking particles, and a smaller fraction still is goes down into the abyssal depths, where it can be kept away from the atmosphere on very long timescales. The exported fraction here can be isolated from the atmosphere on timescales from years to decades, and then here much longer. The MEDUSA biogeochemistry model is designed to represent the key processes involved. It's a relatively simple ecosystem model that's been selected as the biogeochemistry component of the new UK Earth System model, UK ESM1. It represents the planktonic organisms by 4 compartments, 2 size classes of zooplankton and 2 size classes of phytoplankton. This division into different size classes allows us to represent slow and fast sinking fluxes of biological material which are observed in nature. There are 7 traces in the model which follow the fluid motion, 7 passive traces representing the live plankton and nutrients of various kinds. And there's also a semi-passive tracer which is organic detritus, which also undergoes gravitational sinking. The main currency is nitrogen. Nitrogen is the main limiting component for phytoplankton growth, main limiting element for phytoplankton growth. And this is used as the main currency for the biological compartments. And then flows of iron and carbon are inferred by fixed ratios for the organic compartments. And then we also track chlorophyll and silicon, which are in the phytoplankton only. There are 2 chlorophyll traces, one for each phytoplankton type, and a diatom and a silicon tracer for the diatoms. And the chlorophyll to nitrogen ratios and the silicon to nitrogen ratios vary in each of the phytoplankton types. So that requires another 3 traces. So there are 11 traces in all and 60 adjustable parameters. This model is coupled with the NEMO ocean circulation model, and we run in this experiment we run at 1 degree horizontal resolution. The model will be run as standard at a 1/4 degree resolution for UK ESM1, and higher resolutions than that are desirable for biogeochemistry, because we know that the biogeochemical processes are sensitive to mesoscale and sub-mesoscale processes that aren't resolved at a 1/4 degree. These maps represent the seasonal maps of primary production and sinking particle flux for northern and southern hemisphere summers. And this represents model behavior for the default parameter set. We want to explore this behavior over the whole parameter space and try and constrain that using observations. The problem is that 3D models are very computationally expensive. For effective calibration, we need to be evaluating thousands of parameter vectors. So for our 1 degree model, we can perhaps, in a practical experiment, investigate tens of parameter vectors. And as soon as we start to resolve important processes at higher resolutions, that drops off very quickly. Fortunately, a lot of the biogeochemistry can be captured in 1D simulators. So we can use an array of 1D simulators to evaluate quickly hundreds or thousands of parameter vectors. But we then, for inference about the target model parameters, or 3D model parameters, we then need to quantify the uncertainty of the simulators with respect to the target model. So I call our 1D simulator array plus its uncertainty quantification, I refer to as a mechanistic emulator. We can then combine site-based time series from the emulator with observations to get an implausibility function. This is essentially an inverted likelihood function, which we can use for history matching or calibration. This needs to include the simulator error, or uncertainties due to the simulator error, and uncertainties due to observation error. And it should also include uncertainties due to model discrepancy in the target model, which might be due to factors such as structural error or errors in the atmospheric forcing of the ocean model. If we then want to do a more comprehensive analysis in parameter space, we can use training data from the mechanistic emulator to train statistical emulators, which interpolate the function in parameter space, and then we have an implausibility function which also includes the interpolation error. I'm going to set the interpolation error. So I'm not going to talk about all that. This talk's going to be about constructing an experimental mechanistic emulator and evaluating its evaluating its ability to reproduce values from the target model and attach reliable uncertainty estimates to those for use in implausibility or likelihood functions. So each of our 1D simulators in our 1D simulator array represents the evolution of the Medusa, the Medusa biogeochemical traces in one water column at one site. So this is represented by this equation here, in which the terms on the top are the vertical redistribution of the tracer by the fluid motion, and also for the slow sinking detritus by gravitational sinking, this term here. The SMS, or source minus sink term, is the MEDUSA biogeochemistry, and also includes implicit modeling of the fast sinking detritus. And our final term, P, represents the effect of horizontal fluxes. This is a function of an external perturbation that we introduce and the local state C. So this gives an overview of the inputs to the simulator, as well as the adjustable parameters, which are called X. We have environment data, which is the environment to which the biogeochemistry responds. This comprises physical forcing, some of which, for instance, vertical diffusion coefficient is defined as a depth profile, so varies with depth. Others, such as solar irradiance, are only defined at the surface. The physical environment is not dependent on the model parameters, but we also require a biogeochemical environment that is. So this consists of the initial state and the horizontal perturbations. Horizontal perturbations we define for the eight original tracers. Tracers that are linked to those through composition ratios. Their perturbations are then defined by that ratio, which varies with the dynamics. So the initial state together and the horizontal flux perturbations define a biogeochemical environment vector, B, which is parameter dependent. We set all this up in our testbed called MarMOT, which we developed as an open source software tool for model analysis. MarMOT includes a versatile data management system, which handles complex input data sets. And we use this to set up multi-site simulations, multi-site ensemble simulations with different instances of the parameter vector X and different instances of the biogeochemical environment vector B. We evaluate the performance of our simulator array for two different versions of the simulator, which I'll call informed and uninformed simulators. In the informed simulator, we use the parameter-specific environment. So the environment here is specific to our trial parameter vector XO. This isn't a normal situation. Normally, we'll be trying to evaluate or trying to reproduce the target model values for unknown trial parameters. And so we don't know the parameter-specific environment because we don't have a 3D simulation for it. So we need to use the uninformed simulator, where we replace B by B bar, which is a mean environment, which is the expectation of the environment over the parameter space of interest. One of the key data sets for calibration is satellite chlorophyll data, and this shows annual mean chlorophyll from 1998. This data is available everywhere, so we can pick an arbitrary array of sites and we can tailor the number of sites according to the computing resources available. And for our experiment, we set up 12 sites in MarMOT to cover a range of oceanic conditions, and we run the model at these sites for 2 years to simulate chlorophyll in the 1998 target year. Physical forcing is taken from the 3D target model, and for the biogeochemical environment, we use a perturbed parameter ensemble of the target model, which we run for 4 years just to try and reduce any of the major transients in the upper ocean dynamics. This shows records from the 3D ensemble for 10 different parameter vectors. This is our reference sample. So these are records for 1998 at each of the sites. The 10 parameters are drawn from an 8-dimensional parameter space. And you remember there's 60 adjustable parameters in the model. We choose these 8 parameters in a 2-stage process. First of all, we choose 28 parameters which we know are relevant to the seasonal dynamics in the upper ocean. And then from that, we choose 8 parameters which dominate which have the dominant effect on primary production and sinking particle flux. And we do that via sensitivity analysis. So you can see there's a lot of parametric variation there, particularly if you note that chlorophyll is plotted on a log axis. And that shows there's plenty of scope for constraining the model behavior using the satellite chlorophyll records. This shows the performance of our simulator array against the target model for 5-day mean chlorophyll values for 1998. The colors there match the parameter, show the parameter vectors matching the colors on the previous slide. So we've got informed and uninformed simulator arrays shown here. And you can see that, as you might expect, the performance for the informed simulator array is a lot better. There's still quite a bit of scatter here, and this is due to basic simulation errors, which are things like averaging, physical forcing, errors in the lateral flux information, and also, to some extent, differences in the solvent numerics. The additional scatter here is due to replacing our parameter-specific environment by our mean environment, B bar. Most published 1D calibration studies in this field ignore the effect of lateral fluxes, and so it's useful to look at what happens if we do that. So here on the left, we've got results when we emit lateral fluxes from our environment vector. And the result on the right is just the one from the previous slide for the uninformed simulator. And you can see the improvement's quite considerable, where the perturbations we're introducing are only due to the effect of advection by ocean currents on the horizontal gradients. They don't include any horizontal diffusion effects. And despite this, and despite the fact that they're not parameter specific, they make a big difference. So for the complete mechanistic emulator, we need not only an estimate of the chlorophyll output at each site location L and each time T, but also an estimate of the corresponding residual distribution. That is the residual epsilon 2, which is the difference between the target model and the simulator. We assume that the chlorophyll residual is log normal at all times and locations, and we then estimate log chlorophyll from the simulator. So we take the log chlorophyll as being the simulator output G, and we estimate time series of means and standard deviations for the residual to get our probability distribution, to describe our probability distribution. We use 2 different methods for doing this. A direct uncertainty quantification method, which relies wholly on comparisons between the target model and the simulator. And in that, the dependency of the distribution of the residuals on the trial parameter vector isn't modeled. We also use an indirect uncertainty quantification method, which uses an uncertainty analysis to quantify the impact of replacing the parameter-specific environment by the mean environment. This is less reliable on this is less reliant on our truth sample, and also we include a model of parameter dependency, albeit at the expense of a little more computation type for each of our trial parameter vectors. So This flow diagram shows how we get the residual statistics for the direct uncertainty quantification method. The residual statistics are calculated from differences between the target model and the simulator. Now, in a practical exercise, we would use our whole available truth set to define these statistics. In this case, we have a slightly different situation because we want to use available truth to test the method. And so we run 10 separate experiments for each trial parameter in which we use the other 9 parameter vectors to obtain our residual statistics. So for parameter vector xi, we use the 9 other vectors xj, take the target model results for those, get the equivalent uninformed simulator results, and remember that the uninformed simulator requires a mean environment which must be independent, and so that's based on the other 8 parameter vectors. So we end up from our 10-member ensemble for the target model, we end up taking 9 subsamples of 9 different ensembles of 8 members to get the environment vectors. In the indirect uncertainty quantification approach, we divide the uninformed simulator residual into 2 components. The parametric environment residual, which is the effect of replacing the parameter-specific environment by the mean environment, and that's represented, or that's defined by the first 2 terms here. And the mean environment simulation residual, which is the basic simulation error, The term in the middle here, you'll notice, cancels, leaving the usual expression for the residual f of xo minus g. This term here is the output of a perfect simulator. It's a hypothetical simulator, and its environmental input is the expectation of the true 3D model environment over the parameter space. So we can think of that as a true mean environment simulation. So the parametric environment residual is the difference between the target model and the true mean environment simulation. And the mean environment simulation residual is the difference between the true mean environment simulation and our approximation to that from the uninformed simulator. So we need to estimate the statistics for these 2 residuals. For the mean environment simulation residual, it's due to basic simulation error, and so we pragmatically assume that that's identically distributed to the informed simulator residual. For the parametric environment residual, we do an uncertainty analysis in which we estimate these 2 terms using the simulator, and we assume that the difference in estimates is independent of basic simulation errors. This term is approximated simply by our uninformed simulator estimate. The distribution of f we estimate by running the simulator with multiple realizations of the unknown environment, and these are taken from a statistical model. And the statistical model is based on our 3D target model ensemble. It gives the mean environments B bar for the uninformed simulator array, and it includes a stochastic environment generator to generate our environmental realizations. This is derived from an EOF analysis of the target model. Output for the various environmental inputs. Dependencies between the different sites are ignored. We also ignore any dependencies between the initial state and the lateral flux perturbations. But we preserve covariances between the concentrations of the different tracers and the different tracer concentrations at different depths. For the lateral flux perturbations, we also preserve covariances in time as well. So this shows the processing for the indirect uncertainty quantification method. You can see the basic simulation residual stats are calculated along the top, and the parametric environment residual stats on the bottom. The environment stats are parameter dependent, and the parameter dependent processing is shown in green. And see G here is a function of xi, our parameter. Allowing for this parameter dependency potentially gives us more accurate statistics, but it does introduce a computational overhead. This environment uncertainty ensemble is a 1D ensemble run that we use for our uncertainty analysis, and the input to that is 100 different environment vectors generated by our statistical environment model. So we have 100 members. We could possibly reduce that, but we haven't experimented with that yet. So this shows some results. These are for two contrasting sites. At 60 North, we have strong seasonal cycling. We have high nutrients. We have strong light limitation in the winter. 30 North, in contrast, we have low nutrients and much more light availability. So these are the results for the two different methods in the top panel, and for the indirect method, the two different components in the bottom panel. The means are shown on the left here and standard deviations on the right. I'm going to concentrate on the standard deviations. You can see at 60 North, there's massive differences between the two methods early on, at the beginning of 1997, but these have pretty much disappeared by 1998. Also note that the indirect uncertainty quantification method gives much lower uncertainties at 30 North. Looking at the component residuals, you can see that the parametric environment residual tends to dominate at the southern station, whereas at the northern station, the simulation error tends to dominate. Now, the reason for this is there's much stronger local dynamics at 60 North, driven by the strong seasonal forcing. We test the robustness of the emulator by comparing actual error distributions with those predicted. And here I've normalized the error so that the predicted distribution comes out with zero mean and unit standard deviation. The actual error is shown in blue, and blue and red. The actual error for the direct uncertainty quantification in blue shows that the emulator is quite robust. It does fairly well at all the stations. With the indirect uncertainty quantification, we get quite a bit of underestimation of uncertainty, particularly at 35 North, 25 North here. And these tend to be the stations, or some of the stations at which the seasonal cycles are much weaker, and they're lower nutrient stations. To look a little more at what's going on, we can plot time series of the normalized error for the different parameter vectors. And you can see at 60 North, although with the indirect uncertainty quantification method, there's very large errors at the beginning, these go way off scale. Actually, when we get to the target year, 1998, we're actually doing a bit better than with the direct method. Now, the reason for this is that because of the strong seasonal dynamics, there's very little memory in the system comparatively. whereas at the more southerly site, although the indirect uncertainty quantification method doesn't do quite so badly early on, there's a definite temporal autocorrelation in the errors, and the error persists. So the indirect uncertainty quantification method doesn't perform so well at the moment, but we're reluctant to abandon it because of its flexibility being much less reliant on our available truths. And this is likely to be very important at higher resolutions where we have much less truth data available. So we've identified scope for improvement, and one of the important things we think is to improve the characterization of the initial state uncertainty and also allow for covariance between errors in the lateral flux perturbations and the initial state. And we can also improve the basic simulation scheme by improving our lateral flux perturbations in terms of their concentration dependency and improving the forcing data. And this should reduce our basic simulation error component still further, and also that would reduce any potential for interaction between the two error components, which we don't actually allow for in our uncertainty quantification. So to conclude, we've got a prototype mechanistic emulator that demonstrates a couple of fundamental improvements in our site-based modeling capability, one of which is the effective representation of the lateral fluxes, and the second is quantification of 1D simulator uncertainty, which hasn't been done for this sort of model before. We can easily extend our 1D approach to higher resolution models, and this reduces the need for trade-offs between resolution and ensemble size. And this will allow for rapid evaluation of hundreds to thousands of parameter vectors, which we can then use to build statistical emulators for more comprehensive analyses. And overall, these methods should provide a means of getting much more effective use for our ocean data to improve global biogeochemical models and improve uncertainty in their predictions. Thank you.
Okay, any questions?
Yeah, so I'm not sure if I missed this in the talk, but what sort of statistical emulators would you use?
Well, it's not something that we've looked into in much detail yet, but Gaussian process models, something like that, that would be a first approach. But we haven't tried yet, so we don't know how useful that will be.
Okay, thanks again.
Yeah.